All right, so in this video, we're going to show you a little bit about ions and teach you how to recognize ions in their two different forms, which is both negative and positive. The major misconception of this particular chapter with ions is just knowing those definitions. A cute way to remember one of those is that positive ions have positive looking charges in their definition of cation. You could also remember that cats, they have little paws, and if that helps you realize positive charge, then kind of weird, but if that helps, it helps. And then anions are negative. What we see about size is that things get larger in this kind of down and away category. So notice our smallest is helium, our largest down here is cesium. So things get bigger as we go left and as we go down. That is our size trend of the periodic table. And this goes for positive cations and as well as negative anions. Anions tend to be smaller, cations tend to be larger. And that's what we see here on this particular page. As we look at ions, we mentioned this already, which is a good icebreaker for this particular chapter. Notice we're not showing mass numbers because that's a little overkill. You will see them in the homework though. But an atomic number is rarely shown on that lower left. So notice no lower left or upper left kinds of numbers at all. All we really see is those charges on the right. And the easiest way to think about charge and not make mistakes is think about protons and then you subtract electrons. So notice over here, if we have anions, those are negative, these are just going to have more electrons than protons. So if you have more negative than you have positive, you end up negative. Obviously, neutral just means that your protons are equal to your electrons. Over here, it just means you have more protons and you have less electrons. So if you have more positive protons than electrons, notice you stay positive as a result. So it's keeping track of that idea. If you want to think about the periodic table, it's all relative to their noble gas. So let's imagine for a minute that we show you a generic periodic table. As crude as that may look, we have that long kind of rectangular group there. We have that middle rectangle there. We have that kind of square shape over here. We have that metalloid line that kind of breaks down through there. And then your noble gases. So what's unique about the periodic table and ions is in their current position, they're neutral. But everybody wants to be like the noble gases. So the trick then is, how do we feel like a noble gas? Well, if you're a metal, you're going to be typically on the left of that dark line. So metals that are in, say, group 1 or 2 are in families like 3 or 4 or 5 underneath. They're going to go to the left to be like their previous noble gas, because the distance in traveling left 1 box versus forward either 7 or 17 blocks is a whole lot easier. So for that reason, this entire family is going to be positive 1, because they're going to lose 1 electron to be like their previous noble gas. These guys will be plus 2 because they're going to lose 2. These guys plus 3, plus 4, plus 5, and so forth. The only ones that we really deal with in introchem are specifically the ones in the 2s, a little bit of the 3s, a little bit of the 4s, but after that, intro chem kind of stops because that's when it starts to break a few of the rules that we want to pretend don't get broken in intro chem. The opposite is also true for nonmetals. If you're, say, a halogen over here, you're just going to move over 1 if you're in, say, group 17. So if you're going to move over 1 in position, that means you're going to have to gain electrons. So if you're gaining 1 electron, that's going to make you negative because your electron's negative. So these guys are going to be -1. These guys will gain 2, -2, -3, -4, and so forth. And again, that's the ones that we tend to focus on, the ones that follow the rules for the most part. So in summary, what we can see is if you're moving to the right to a noble gas, you're going to become negative. Every group you move is a negative charge. And then the opposite is true, that if you're going to be moving left in the periodic table, you're going to become positive. And every family you move, you're going to be a +1 for each of those families. Again, we're ignoring the noble gas, or the transition metals, because those are a mess. So as we start to pair up some symbols, start to think about what are their charges, and then what we're going to do with these charges is cross them. If they're different, if they're the same, we're just going to put them together. So let's look at some of these based on what we just showed you on our previous slide. So again, sodium in group 1. So let's do those cations first. If they're in group 1, they're going to move left, and they're going to become a +1. So we're going to expect to see a +1 for sodium. It's going to go left. Magnesium is going to go left twice to be like its previous noble gas. Aluminum, back 3 groups. Lithium is going to go back 1 group. And then carbon has a choice of going forwards or backwards, technically speaking. Because oxygen is going to be negative, we're going to pretend that it's positive. But either way, it's 4 to the right or 4 to the left. So even if you're not sure on that one, it's a 4 either way. In this situation, though, it'll have to be a 4+ to deal with oxygen's negative. Now as we look at the anions, in the anions we want to think about how far to the right do they go. So with fluorine, we want to go to the right once, so -1. Oxygen going to go as a chalcogen over twice to be -2. Sulfur in the same family but a little bit lower, going to be also a -2, same family, same charge. That was also the case for sodium and lithium in the previous column. Nitrogen going to go over 3. And oxygen, we already had with our second example, going to go over 2 again. So then as we make the compounds, we have to realize that these charges are either the same or different. So in the situation with these first couple examples, you're going to see that 1 and 1 cancel. So we would just get Na and then F. Even here, 2 and 2 cancel. So we get Mg and O. But when the charges are different, there's algebra involved, but algebra can be forgotten if we just take these numbers and cross them over. So if aluminum was a +3 and sulfur is a -2, just take the 2 over. So take this 2 over, take this 3 over, and notice we get Al twice, sulfur 3 times. What it did for us is it basically said that 3 times a 2 is a +6, and it said 2 times a 3 is a -6, and those cancel. So this is the crossover rule, and it's the fastest way to make compounds from anions when the charges are different. So we can do the same thing here. If lithium is a +1, and this is a -3, cross the 3, cross the 1. So this would be lithium 3 times, and then nitrogen only once. The ones are kind of redundant, but when you see this section in the homework, you're going to see that they're going to a 101 in that matching kind of section. Why did that work? Well, if you do a +1 3 times, you get a +3. If you do a -1, if you do a -3 one time, you get a -3, and then those cancel. Lastly, we get a 4 and a 2. So if we have a 4 and a 2, you cross the 2, you cross the 4. So what happens in this situation, at least initially, you get C2O4. Hopefully then you realize that your charges did cancel because you had 2 positive 4s, which is a -8. And you have a -2 times now a 4, which is, whoops, that was a +8. The -8 and -8 and +8 cancel. And there's only one mistake, because the mistake here is that 2s and 4s can be reduced. So you can reduce a 2 and a 4 to a 1 and a 2, and that's why we get carbon dioxide. So the actual answer there is really CO2, because you can reduce a 1 and a 4. So anytime we cross charges, just make sure that you, when you cross, you look for things that can be reduced, and that was the case for only carbon dioxide example. The other ones we had either exactly the same charge or charges that couldn't reduce any further. Last thing I'm going to mention is ionization energy. This is the energy required to remove one electron. And for some elements, that's very easy. For other elements, that's very difficult. As is the case for the left of the periodic table, those are the losers. Metals like to lose electrons to become positive, so their energy is very low, because that's exactly what they want to do, and it doesn't take a lot of energy to remove the electron that they wanted to lose anyway. However, if you go to the right of the periodic table, those elements want to gain electrons. The last thing they want to do is lose electrons, so their energy is very high. So what we see from this particular page here is a reflection of that concept, because if we have a generic periodic table, so here's a very crude periodic table, notice all of our noble gases. Those guys are the highest of their specific period, and they're all over here in this region right here. So definitely energy goes up as we get to a noble gas, because they're full. They don't want to lose any, obviously, because that would make them have that empty spot in their outer shell of electrons. However, something unique also shows up, and that's that fluorine is so high in energy. Notice fluorine is higher than all the larger noble gases too. So what we're seeing is energy actually gets higher in the opposite direction of size. So ionization energy goes up and to the right, and that's because small atoms have fewer electrons, so losing one of them is a bigger deal. Imagine, for example, that you're helium. Helium has 2 electrons. Imagine that's 2 children. If you take 2 children to the mall, you expect to leave with 2 children when you leave the mall, right? Losing one of your 2 children is a big deal. However, if you're radon and you have, say, 80 plus kids, right? Then if you take 80 plus kids to the mall, losing one of those, would you even know, right? Just the vast number of electrons that you have when you're larger, losing one of 80 plus is not near as big a deal as, say, losing one of 2. So the percentage of loss for radon is a whole lot less than the percentage of loss for helium or for, say, fluorine. And that's why the ion energy goes up. Fewer electrons, losing some of those fewer electrons is a bigger deal. As we look forward to our next chapter, we're going to have to better understand electrons and how they fit into this stadium analogy that we've been using for the last several videos. So we'll do that using light. light can show us the difference between these different levels based on the wavelength of light and the energy that's produced therein. So we can look at atoms, look at the light that they produce to know what their stadiums look like and where those electrons are potentially sitting. See you next time.